So the next part is about cooperative uplink communication. You can see this also led to a paper in 2008. Even though it's already more than 12 years ago, it's still interesting to see how you can use cooperation even in the lower layers of the ISO-OSI model. So the idea is here that if I want to send something from the right device over here to a base station and also something to my neighboring device, normally I would do this in the TDMA fashion. So I would first send to the base station and then send to the to my neighboring device. Question is, of course, can I do this at the same time? And there is a way how you could possibly do this if you have an assumption that the cellular link is far away and your short-range communication is very close with you. What you could do is you take a, for example, 16 QAM modulation, and what you see here that seems a little bit strangely originated. What you can do, you instead of placing it equidistant, now you're moving some of the points to the left upper corner, to the right upper corner, to the left lower corner, and to the right lower corner. So it's called heterogeneous QAM. That they're sometimes doing also DVB-T for heterogeneous transmission of some frames they want to protect more than others. So if you do this and you look at a bit error probability of such a approach, it will be always higher than if you would have a 16 QAM approach, because here the interference is quite high. But what we will do is now we will modulate our signals to the base station and to the short-range device in the same time. So the first 2 bits will tell me the first 2 bits of the stream to the cellular will tell me in which of the corners am I, right? And then with the next 2 bits from the for the mobile device next to me, I will say in which region I'm here. So if the stream of the to the base station will say, for example, 0, 0, I go upper left, for example. And then I'm here at this center position. And then the next one will say, for the device next to me, it's also 0, 0. Then I go up again to the corner over here. So the first 2 bits will just say which center frequency I will have to say. And the next 2 bits will say which local phase and frequency I should take here, right? So in the end, you get to, when you send something out, it looks exactly like this 16 QAM with the corners over here. Now, if you send it out, what the base station will see, it looks like a 4 QAM. And you just receive it as a 4 QAM, and it doesn't matter it was this, this, or this, it's just a 4 QAM. Because we just used the center frequency out of the 4 2 bits, everything is fine. And at the same time, here the mobile device next to it will receive all 16, but it doesn't matter in which of the corners you are. You just want to have the local phase of that. So what you can do is you can overlay them again, and you get a 4 QAM out of that as well. And this is the way how you can get a very good uplink communication in the or cooperative uplink for the base station and the device at the same time, which will help us a little bit more to decrease the cost of the cooperation. Here are some results showing that the symbol error ratio is more or less the same, whether you do the which kind of modulation you do. I think the new approach is a little bit higher for the, if you take a 4 QAM with a 16 QAM, it's more or less the same. Good. If you talk about combined cooperative air interfaces, that was one specific one, but we did, for example, in Bluetooth, when we do it with Bluetooth, we always use the short range in a TDMA, and the other one is totally orthogonal to it. But what if we would have a combined air interface? So what we would think about is something like an OFDM-A-based air interface, and we say, okay, we just take subcarriers, and the base station will say, okay, I need to send data to 3 of the devices. I will allocate some subcarriers for that and leave some subcarriers unused that they can use later for local exchange, right? So the base station is not only distributing the content, it's also managing the subcarrier that will be used for the communication. Now, this kind of communication, because there are larger distances, the modulation coding factor is here 1, while it can be a little bit larger when you use the short-range communication over here, right? So how can this be done? So think about the subcarriers. If you have a certain number of subcarriers here, the complexity is nothing else than n log n, where n is the number of subcarriers. This is if you're only cellular. If you just say I am cellular plus I have some short-range subcarriers more for my short-range communication, and I have it orthogonal to each other, then you see the complexity will even increase. But if you could dynamically assign subcarriers for cellular and short-range in a dynamic way, the complexity will be more or less the same. And interesting is now how to shift the number of subcarriers for one or the others. We could show that if you have 4 cooperating entities, then you have 16 times higher spectral efficiency. So that gives you a 65% complexity reduction. The reason for that is because if you have one cooperating cluster, you would say, okay, I only need half of my cellular short range, and then I need some subcarriers to send out something and something to receive. And now it depends how much more efficient is this communication than the other one. And if this time was 16 times higher, that's really good. So I get a lot of data rate done here, and I don't need all of these subcarriers anymore. I need half of that for cellular, for sure, because I need half of that of the service. The other one needs also half, and then we see what we have to do and how far they are together, etc. pp. If I then have 4 devices, I need only 25% of the subcarriers for the cellular and some of them for the short-range communication. Good. Something I also would like to highlight was the cooperative task scheduling. We already talked about this as an idea. Here's some numbers. This was one of the book chapters we wrote, and it all started with the idea of something called dynamic voltage scaling. And this was for a laptop with an Intel laptop at the time. You had 2 CPUs. They were with a wired bus over here, and what you could do is you could put a different task on the CPUs, and what you would like to do is share the task in a way to reduce the clock rate. Why should you do that? Here you see the power over the frequency for an analog device, ADSP, and some clock rate over here, and you see if you run at full clock rate, 600 megahertz, then you use 275 milliwatt. If you then would work only with half of the clock rate, then you would only use 80 millivolts. But then if you have half the rate, you would need twice the time. But if you can give half of the task to the other side and you work in parallel, then the task would be finished at the same time, but you need twice the amount. And now you have twice the amount, it would be 160 milliwatt, which is still less than the 275. Here, if you have 3 devices, you need so 1/3 of the rate, but 3 devices, 150 milliwatt. And here, if you have 4 devices, you see it goes up again. Then the best seems to be to have 3 devices over here. Good. But this is when you have a wired bus between them. What would happen if you have a wireless link between them? Then you would see that here's the energy that you will use over the distribution of the task, and then you can see what I have to pay as a price to communicate with the other side. So the blue curve is more or less what you would have if it would be wired, so without a cost. So you could say I'm doing the job my own, I can give it 50% to the other side, or I give it fully to the other side. Then it's more or less the same. But you see, the best is if we share it 50-50, then you need only 60% of the energy consumption. Now, if you have a price on this wireless link, for example, 5%, this is the blue line, you see, if I give it to the other side fully, I would have to pay 10% more energy, because this is the cost of bringing it over to that side and coming back twice 5%, and then twice 10%, 50%, and so on. So the more it costs, the more it will be shifted. But also the operational point, when you have the minimum, here we have the minimum of 50%. Here it seems to be already 40%, right? And here's it goes down to 40% more or less when you have the optimal point of sharing. So just give 40% to the other side. And you see that you will not gain as much as this 60%. You can only go down to 75%. This is because now you have a cost on this wireless link. Good. Last but not least, you could even have something like a beamformer. Now you're at the antenna level. It's a work that we also did in Aalborg. It's called Cooperative Antenna Beamforming. The idea is, instead of sending omnidirectional beams where you block all the others with your RDS CDS, why not trying to get access points which are orthogonal to each other and then getting more data rate? This was something we investigated also for security reasons. It was also a nice project, also 2003, and we built this beamformer on a laptop where we replaced the normal omnidirectional antenna with a passive phase shifter and doing some beams. Interesting was how many beams you can get out of it. We selected 16 of the beams and then just said pick one of the 16 to optimize the performance. Then there you see the user interface. You see here what we can get out when you have an omnidirectional or when you have a directed beam. And this is the signal strength, and this is the data rate. And we see here in this example, you had nearly 3 times the data rate that you have with an omnidirectional one. So this was quite interesting. Here you see the beam pattern that we used. So currently we did an omnidirectional testing. So the question is now how much you can get out if you do it at the same time. So either you take the links and you see I could send at the different time slots, not to interfere, those TDMA-based medium access, or I can also send at the same time. But you will have some interference to the other side. And here's something like the cooperative beamforming with the gains you can get out of it, depending on the SNRs on the 2 different links, right? So if you have a very good link down here and a very bad link on the other one, the gain is quite high for this guy and the other way around as well. So this is for the capacity, and this is also for the energy. Now there are certain ways you can gain in capacity and in energy, and you see the values are quite high with 35 to 39% in doing this cooperative beamforming. I will not go into detail, but just as an example how low you can go for cooperative stuff. With that, I would like to finish the motivational speech for cooperation, and in the next lecture we really will find out how to calculate energy gains for cooperative clusters.